Welcome, curious minds, to the deep dive. Today, we're not just scratching the surface, we're really launching ourselves out there, way out, into the cold, mysterious depths of our solar system, our target, one of the most peculiar residents, Uranus. What actually makes this ice giant such a captivating enigma? And, what surprising secrets are we hoping to pull from its distant, kind of sideways existence? Okay, let's unpack this. We're going to peel back the layers on, well, everything. From its accidental discovery, the dramatic myths behind its name, and even this weird cosmic bad day that kind of skewed our scientific understanding for decades. Seriously. Get ready to explore its extreme tilt, its potential hidden oceans, and the ambitious missions getting ready to finally pull us closer.
Yeah, and what's fascinating here is just how much our understanding of Uranus has evolved, despite it being so incredibly far away and observed so briefly up close. This isn't just about some cold, distant planet. It's really a story about discovery itself, the slow, persistent march of science over centuries, and how a single fleeting snapshot that Voyager 2 flyby can be, well, deeply misleading. It also highlights why these ice giants, Uranus and its sibling Neptune, are becoming so critical to understanding the bigger picture, especially with all the exoplanets we're finding out there. We piece together a lot of information painstakingly, but mysteries definitely persist. And that's what's driving scientists, towards the next generation of exploration with real anticipation.
Exactly. And that historical context is so important, isn't it? To really appreciate Uranus, we need to rewind, like way back. For thousands of years, humanity only knew 6 planets. Just imagine that. Mercury, Venus, Earth, Jupiter, Saturn. That was it. That was the whole known planetary neighborhood. Anything beyond Saturn, just darkness, unknown. And what's even wilder is that Uranus itself, well, it was seen many, many times before anyone twigged what it actually was. We're talking observations maybe going back to Hipparchus in 128 BC. Possibly. But definitely, John Flamsteed, the first astronomer royal, he cataloged it in 1690 as a star, 34 Tauri. And then Pierre-Charles Monnier, a French astronomer, he logged it at least 12 times between 1750 and 1769. But every time, they just thought it was a faint star. Why was it so tricky to spot, even for these really skilled observers?
Well, it really speaks to the limits of observation back then, even for diligent astronomers without really powerful telescopes. These guys were meticulous, no doubt. But Uranus is just incredibly dim from Earth, and it moves so slowly against the background stars. That slow, stately pace, combined with its faintness, it made it almost impossible to distinguish its tiny disc-like shape from just a point of light, a star, especially with the telescopes they had. To them, yeah, just another fixed point, until William Herschel. Now, he was quite a figure. Born Friedrich Wilhelm Herschel in Hanover, Germany, 1738. He actually moved to London in 1757 as a musician. A very talented one, apparently. He was even the organist at Bath Abbey. But his real passion became astronomy. And he wasn't just observing, he started building his own telescopes. In Bath, England. Really powerful reflecting telescopes, pushing the limits of optics at the time. His skill as a craftsman was just as important as his eye.
A master musician and a master telescope maker. Wow, a true Renaissance man. That's incredible. So how did this self-made astronomer, systematically scanning the skies, how did he finally break through where others hadn't?
Right. So on March 13th, 1781, he was meticulously surveying the constellation Gemini. He was very systematic about his work, and he spotted this faint object that just looked different. A bit hazy, maybe. Not quite the sharp point of a star. So he observed it again over several nights, and crucially, he saw it move, clearly moving relative to the background stars. That's the dead giveaway, isn't it? Something much closer than the distant stars. Initially, he thought it was a comet, which was reasonable. Comets move. He reported it as such on April 26, 1781, but then other astronomers across Europe started looking at it too, and they calculated its orbit precisely. Turned out it wasn't a comet's long, stretched-out path. It was a nearly circular orbit, way, way beyond Saturn. That clinched it. It was a planet. A completely new world. And this discovery host, it was just monumental. It literally expanded the known boundaries of our solar system for the first time in recorded history. It effectively doubled the size of the known solar system. Just think about that. It changed everything.
Wow, doubling the solar system overnight. That's a huge mental shift. And okay, as the discoverer, Herschel gets the naming rights. A big deal. What name did he want for his incredible discovery? Did it stick?
Well, Herschel was, living in England, grateful to his monarch. So he proposed Georgium Cetus, George's star, in honor of King George III. And yeah, English astronomers were pretty happy with that initially.
George's star doesn't quite roll off the tongue like Mars or Jupiter, does it?
Maybe not. And astronomers elsewhere, particularly in Europe, they weren't so keen. They preferred sticking to the tradition. Naming planets after figures from classical mythology. It was the German astronomer Johann Bode who really pushed for Uranus. And his logic was actually quite neat if you think about the mythological family tree they knew then. Mars and Venus, children of Jupiter or Zeus. Jupiter, son of Saturn or Cronus. And Saturn, well, he was the son of Uranus, so it fit perfectly, completed the lineage.
Ah, okay. It slots right in.
Exactly. And so by the mid-19th century, Uranus was the name everyone agreed on.
So, sorry, King George, no star for you. We got Uranus instead. Which, let's be honest, probably caused a few giggles in classrooms over the years.
Oh, undoubtedly. It's given generations of science teachers a moment of slight awkwardness, I'm sure.
But beyond the name itself, that mythology you mentioned, Bode picking the father of Saturn, it connects to a pretty powerful, and you said disturbing, myth. How did that specific story become the name, and what makes Uranus unique in how we name planets?
Right. Well, putting the pronunciation jokes aside, the name Uranus is unique. It's the only major planet named directly after a Greek god, Uranus. All the others used the Roman names: Jupiter, Saturn, Mars, Venus, Mercury, all Roman equivalents. Uranus' Roman counterpart would be Caelus, but we stick with the Greek. And in Greek myth, Uranus isn't just a sky god. He is the sky. The primordial personification of the heavens. He's ancient, foundational. Son and husband of Gaia, Mother Earth. Together they birthed the first Titans, including Cronus, who the Romans call Saturn, and also the Cyclops and the Hecatoncheires, these hundred-handed giants.
So not just a god, but like a cosmic force, an elemental being. Wow. But you mentioned disturbing myth. What actually happened to this primordial sky god? It wasn't a happy ending, I take it?
No, not at all. The mythology is quite dramatic and really foundational for the whole Greek pantheon. Uranus was apparently a pretty terrible father, cruel, oppressive. He hated some of his children, especially the Cyclops and the Hecatoncheires, because they looked, well, monstrous. So he hid them away deep inside Gaia, inside the earth, causing her immense pain. Gaia, suffering, made this sickle out of flint or adamant and begged her children to punish their father. Only Cronus, Saturn, was brave enough or maybe ruthless enough to do it. He ambushed Uranus and, well, castrated him, threw the severed parts into the sea.
Whoa. Okay, that's great.
It is. And according to the poet Hesiod, from the sea foam that spread around those parts, Aphrodite, the goddess of love, was born. But that act overthrew Uranus, ended his reign, and brought in the age of the Titans, led by Cronus. A really pivotal, violent moment in their cosmology. So yeah, the name Uranus carries this deep, dramatic backstory. Power, creation, rebellion. A pretty grand, if dark, namesake for this distant, mysterious planet. Here's where it gets really interesting.
Definitely a heavy name. Okay, from those ancient dramatic origins, let's rocket forward to the planet itself. We've traced the history, the mythology. Now let's really meet this peculiar world. Expert, give us the basics. What are some of the standout stats for Uranus? What jumps out immediately? Name aside.
Okay, stats-wise, Uranus is a giant, no question. It's the third largest planet by diameter, fourth most massive in the solar system. It dwarfs Earth, and it is distant, average distance from the sun. About 2.8 billion kilometers. That's 1.7 billion miles. To give you a feel for that, the sunlight reaching Uranus is only about 1/1400th as intense as what we get here on Earth.
1/400, so it's always twilight there, basically.
Pretty much, yeah. A perpetual dim twilight compared to us. And that distance means its orbit is huge. It takes 84 Earth years to go around the sun just once.
84 years, so a season lasts like 21 Earth years.
Roughly, yeah. Decades-long seasons. But counterintuitively, a Uranian day is actually pretty short, about 17 hours and 14 minutes, faster than Earth's day.
Huh, okay. And its look, that distinctive color.
Ah, yes, that pale, ethereal blue-green color. It's quite beautiful, actually. That comes from methane gas in its upper atmosphere. Methane is really good at absorbing the red part of sunlight and scattering the blue and green light back out into space, which is what we see.
84 years for one orbit, decades-long seasons.
Yeah.
A short day, blue-green. Okay. But the absolute weirdest thing, the thing everyone knows about Uranus, is that tilt. It's tipped on its side.
Yeah.
Can you describe just how extreme that is? And what do scientists think knocked it over?
Oh, it's extreme, Armin. When we say tipped on its side, we mean it. Its axial tilt is about 97.77 degrees. So its axis of rotation, the imaginary pole it spins around, is almost parallel to the plane of its orbit around the sun.
Parallel, not just tilted, a bit like Earth's 23.5 degrees.
Nope, almost flat against its orbital path. It essentially rolls around the sun like a bowling ball rather than spinning upright like a top. And the leading theory for why? A massive collision, probably early in the solar system's history. Imagine something maybe planet-sized, perhaps even twice the size of Earth, slamming into the young Uranus. That kind of catastrophic impact could definitely have knocked it over onto its side like that. A really violent beginning.
A giant cosmic smackdown. Okay, so what does being sideways do to a planet? What are the consequences for its seasons, its weather?
The consequences are profound. It leads to the most extreme seasons imaginable in the solar system. Think about it. Near the solstices, one pole points almost directly at the sun for about 42 Earth years, continuous daylight.
42 years of sun.
Yep. While the other pole is plunged into complete darkness for 42 years.
42 years of night. That's unbelievable.
It is. Only a narrow strip around the equator gets a somewhat rapid day-night cycle during those periods. This extreme heating difference between the lit pole and the dark pole must drive some very strange atmospheric circulation, much different from Earth or Jupiter. And adding to the weirdness, its rotation is retrograde. It spins east to west.
Opposite to Earth and most others?
Exactly. Most planets spin counterclockwise if you look down from above the sun's north pole. Uranus spins clockwise. So extreme tilt and backwards rotation. It really does scream giant impact event, doesn't it? Makes it a fantastic natural laboratory.
Definitely a laboratory for weirdness. Okay, let's dive inside. It's called an ice giant, not a gas giant. What's the difference? What's it actually made of?
Right, ice giant is the key term. Unlike Jupiter and Saturn, which are mostly hydrogen and helium all the way down, Uranus and Neptune have a much larger proportion of heavier elements, especially volatile compounds that astronomers call ices. We're talking water, ammonia, methane. Not necessarily frozen solid like ice cubes, but in different states under immense pressure and heat deeper down.
So no solid surface to stand on.
No, definitely not. The model looks something like this. An outer atmosphere, mostly hydrogen and helium, like the gas giants. Then beneath that, a very deep, thick mantle or ocean. Not liquid water like here, but a hot, dense, soupy mixture of those ices, water, ammonia, methane, behaving like a fluid under extreme pressure. And then probably a small rocky core at the very center, maybe about the size of Earth. Another difference from Jupiter to Saturn is that helium doesn't seem to have settled out towards the core as much. The composition seems more mixed.
Okay, so this deep, soupy, high-pressure interior, what about the atmosphere we can see? If we sent a probe plunging in, what gases would it find? And I heard something about a smell.
Yeah, the smell. An atmospheric probe would face hellish conditions, honestly. The main gases are hydrogen and helium, but there's a good chunk of methane that gives it the color, and then traces of other things. Water vapor, ammonia, some carbon dioxide, carbon monoxide, ethane, acetylene, and yes, hydrogen sulfide. That's the one responsible for the lovely rotten egg smell.
Ew. Okay, good thing we need spacesuits. And it's cold, right? Like really cold.
Incredibly cold. The upper atmosphere hits a minimum of about minus 224 degrees Celsius. That's 49 Kelvin, which actually makes it, in some spots, the coldest planetary atmosphere in the solar system. Colder even than parts of Neptune, though Neptune is colder on average. Plus, the pressure ramps up incredibly fast as you go deeper. It would crush any probe we currently have long before it got near that ocean.
So freezing cold, smelly, crushing pressure. And for a long time, scientists thought it looked kind of bland, featureless. But that wasn't the whole story, was it?
No, that initial impression from early images, even Voyager's first look, was a bit deceiving. That methane haze smooths things out visually. But we've since seen, especially using Hubble and powerful ground telescopes, that Uranus does have dynamic weather, especially around its equinoxes when the sunlight hits the equator more directly. We've seen bright cloud features popping up and disappearing, suggesting storm systems. And the winds are ferocious. Up to 900 kilometers per hour. That's over 560 miles per hour. Hurricane speeds, constantly.
Whoa! And the winds are weird too, right? Going different directions.
Yeah, that's another puzzle. They blade retrograde against the planet's rotation near the equator, but they switch to prograde with the rotation nearer the poles. It's a complex circulation pattern we don't fully understand.
Okay, so storms, crazy winds. What about rings? Saturn's famous for them. Uranus.
Uranus has rings too, just much fainter and darker than Saturn's bright, icy ones, much harder to see. It actually has two distinct sets of rings. We know of 13 rings in total now. They're very thin and composed of dark particles, ranging from dust-sized grains up to maybe small boulders. The thinking is they probably formed from moons that got shattered by impacts or maybe captured asteroids broke up. They don't seem to be leftover material from the planet's formation.
Dark, subtle rings from shattered moons. Okay, how did we even find them if they're so faint?
It was actually a bit of an accident. Back in 1977, scientists were using NASA's Kuiper Airborne Observatory, basically a telescope flying inside a modified cargo plane, a C-141, high above most of the atmospheric interference. They were planning to watch Uranus pass in front of a distant star. an occultation. The star's light would dim as the planet blocked it, letting them study Uranus's atmosphere.
Smart.
Yeah, but what they saw was unexpected. The starlight dimmed slightly, several times, before Uranus even reached it, and then again after it passed.
Whoa. Something else was blocking the light.
Exactly. Those dips were caused by previously unknown rings orbiting the planet, a total surprise discovery. Then later, between 2003 and 2005, the Hubble Space Telescope spotted two more, even fainter, outer rings. So a whole system just very subtle.
Okay, one more weird thing before we get to Voyager 2. The magnetic field, you mentioned Earth's is pretty lined up, comes from the core. Uranus.
Uranus's magnetosphere, that magnetic bubble protecting it, is just bizarre, truly odd. Remember that crazy 98-degree axial tilt? Well, the magnetic field is tilted another 60 degrees relative to that rotation axis.
Wait, so it's tilted relative to the already sideways tilt?
Yep. And not only that, the source of the magnetic field isn't even near the planet's center. It's offset by about a third of the planet's radius.
It's off-center, too.
Off-center and way tilted. Imagine if Earth's magnetic North Pole was somewhere down near, I don't know, Antarctica, and the field originated somewhere under Brazil. It's that kind of weird. This creates a really unstable, wobbly, lopsided magnetic field, which means the auroras on Uranus don't happen neatly near the poles like on Earth. They pop up in strange places and shift around constantly. Interestingly, Neptune has a similarly tilted and offset magnetic field, which makes scientists think maybe this is just how ice giants are.
This raises an important question. Why? Why are ice giant magnetic fields so messed up compared to ours or Jupiter's? What's happening inside?
That's the multi-billion-dollar question, really. It points to fundamental differences in their interiors. The leading idea is that the magnetic field isn't generated deep in a metallic core like Earth's. Instead, it might be generated much shallower within that thick, soupy ocean layer of water, ammonia, and methane. Under the immense pressures there, these molecules might form a conductive state, sometimes called superionic ice, where ions can flow and generate a magnetic field.
Superionic ice? Okay, sounds cool.
It's pretty exotic stuff. And because that layer is likely convecting, turning around, but maybe not in a simple way, it could create this offset tilted field. There are even wilder ideas involving like oceans of liquid diamond deeper down affecting things, but the conductive fluid ocean is the main hypothesis. It really shows how much we still need to learn about what goes on inside these planets.
Okay, so we've got this picture of a tilted, backward spinning, cold, smelly, windy, strangely magnetic planet with faint rings. Pretty remarkable then that almost everything we knew up close for decades came from one quick visit.
Exactly. That brings us to Voyager 2. Its flyby is absolutely central to the Uranus story. January 24th, 1986, that was the date. Voyager 2, having already swung past Jupiter and Saturn, made the only close approach ever to the Uranian system. It came within about 81,500 kilometers, 50,600 miles of the cloud tops. A pretty close shave, relatively speaking.
Just a few hours, right? A quick dash through the system.
Incredibly brief and hectic, yeah. But absolutely critical. Before Voyager, we knew about the tilt, the 5 main moons, those first few rings found in 77, but not much detail. This flyby gave us our first close-up images of the planet, discovered 10 new moons, found 2 more rings, and measured that weird magnetic field. Yeah. It massively increased our knowledge base overnight. It was Voyager's first solo planetary encounter, too, after its trajectory took it away from Saturn.
A true pioneer. But the data it sent back, specifically about that magnetosphere, it caused some real head-scratching, didn't it? It was so baffling.
Yeah, the magnetosphere data was just peculiar. It created a puzzle that lasted nearly 40 years. Voyager 2 confirmed the extreme tilt and offset of the magnetic field like we discussed. Okay, weird but measured. But it also found surprisingly intense belts of trapped electron radiation within the magnetosphere, really energetic particles.
How intense?
Second only to Jupiter's. And Jupiter's radiation belts are notoriously fierce, real hazards for spacecraft. So finding something almost that strong at Uranus was a surprise. But here's the baffling part. Usually strong radiation belts need a source. They need to be constantly replenished by charged particles plasma from the surrounding space environment, or from the planet's moons or atmosphere. But Voyager 2 found the rest of Uranus's magnetosphere to be weirdly empty, almost devoid of the expected plasma.
Okay, hold on. So you've got these super intense radiation belts, like a roaring fire, but almost no fuel, no plasma soup feeding them. That sounds completely wrong.
Exactly. That's precisely why scientists were, quote, flummoxed. It defied the standard models of how magnetospheres work. It was like finding a car engine running full blast but with an empty gas tank. It just didn't compute. It forced scientists to wonder if Uranus was just some kind of bizarre exception to the rules, operating under totally different physics. They came up with some really exotic, complicated theories to try and explain this apparent vacuum magnetosphere. And for decades, this cemented Uranus's reputation as this ultimate outlier, this deep enigma. Scientists genuinely believe they had an incorrect view of what Uranus and its 5 largest moons are normally like. It cast this long shadow.
Wow, a 4-decade mystery based on that one snapshot. So how did they finally crack it? What changed?
Persistence and much better computer models. Just recently, research led by Jamie Jasinski at NASA JPL, published late 2024, finally provided the answer. They went back to that original Voyager 2 data from 1986. But this time, they applied modern, sophisticated computer simulations, models that can simulate the interaction between the solar wind, that stream of particles from the sun, and planetary magnetospheres with far greater detail than was possible back then.
And what did the new models show?
The discovery was amazing. It turns out Voyager 2 didn't see Uranus on a normal day. It flew through just after a particularly strong blast of solar wind. A significant space weather event had hit Uranus. This solar wind squall had dramatically compressed the planet's magnetosphere, pushing its boundaries inward and apparently energizing those radiation belts temporarily, while maybe sweeping out some of the lower energy plasma.
So Voyager 2 just happened to arrive on a really weird day.
Pretty much. The model suggests the conditions Voyager 2 saw only happen about 4% of the time at Uranus.
Only 4%.
Yeah. If Voyager 2 had arrived just a few days earlier or later, it probably would have seen a completely different, more normal, less empty, less intensely radiated magnetosphere. That whole decades-long mystery might never have happened.
That is incredible. A cosmic coincidence, a snapshot on a bad day, shaped our view for 40 years. That really drives home how a single observation point can be misleading, doesn't it?
It absolutely does. This raises an important question, right? How much have we potentially misinterpreted from other brief flybys or limited observations in astronomy? It's a huge lesson in scientific caution. Planetary environments are dynamic, they change. It's like trying to understand Earth's climate by measuring the weather during a single hurricane. You wouldn't get the full picture. It really highlights why we need long-term missions. We need to stay a while, observe these worlds over time, see their cycles, their variations, and it also shows the immense value of revisiting old data with new tools and techniques. Sometimes the answers are buried right there, waiting for us to develop the means to find them.
A powerful lesson. And that dynamic environment doesn't just affect the planet, but its moons too. Uranus has 27 known moons now. And keeping with the theme, they're all named after characters from Shakespeare and Alexander Pope. Not mythology this time. The big 5 are Miranda, Ariel, Umbriel, Titania, and Oberon, going outwards. What's unique about this whole moon system compared to Jupiter's or Saturn's?
Yeah, the naming convention switched to literature, which is interesting. One really striking thing is how little mass there is in the Uranian moon system. It's the least massive moon system of all the giant planets. Get this, the combined mass of all 5 of those main moons, Miranda, Ariel, Umbriel, Titania, Oberon, is less than half the mass of Neptune's single largest moon, Triton.
Less than half of one moon. Wow, they're lightweights.
Relatively speaking, yes.
Right.
It's just maybe different formation scenario, or maybe more material was lost over time. Also remember Uranus's tilt. Because of that, when Voyager 2 flew by, the system was oriented, so the spacecraft really only got good views of the southern hemispheres of these moons. Huge parts of them remain unexplored up close.
So we've only seen half the picture, literally. What are they made of, generally?
They seem to be mostly mixtures of ice and rock. Roughly 50-50 is the general estimate. Mostly water ice, but maybe other ices mixed in. Miranda, the innermost of the big 5, might be a bit different, possibly more ice-rich, maybe with ammonia and CO2 ices too. Suggests a colder, more primitive composition, perhaps.
Okay, a low-mass system, only half seen. Let's talk about what Voyager did see. What are the surfaces like on these Shakespearean worlds? Any standouts?
Oh, they each have their own personality,
Oh,
even from the limited views. Titania is the biggest. It's got craters, sure, but also these big canyons and fault lines cutting across it, signs of tectonic activity. And interestingly, fewer huge craters than you might expect, which suggests its surface might have been repaved or resurfaced somehow, making it look younger. It even has ridges that look a bit like ones on Jupiter's moon, Europa.
Europa-like ridges. Interesting.
Yeah. Oberon, the next one out, looks older, more heavily cratered than Titania, probably less geologically active in its past. Umbriel is perhaps the darkest, and it appears to have the oldest, most battered surface of the bunch, just saturated with craters. A real relic. Ariel, though, is fascinating. It shows loads of evidence for resurfacing, big canyons, smooth plains. It looks like stuff erupted from its interior and flowed across the surface. Some recent studies even look at these trench-like features and wonder if they're like windows to its interior may be caused by stuff pushing up from below. Cryovolcanism, basically ice volcanoes.
Ice volcanoes, cool. Okay, but the one everyone remembers the pictures of is Miranda, the smallest of the big five, but visually nuts.
Miranda is absolutely bizarre, iconic images. Its surface is this completely chaotic jumble. People describe it like a jigsaw puzzle put together wrong, or like it was smashed to pieces and then just loosely reassembled. You've got these weird oval-shaped grooved structures called coronae. They look like racetracks sometimes.
Corona, okay.
Yeah, these seem to be younger terrains, and they're jammed right up against older, heavily cratered areas, all crisscrossed by enormous canyons and fault cliffs. Some of those cliffs are unbelievably huge, like 20 kilometers or 12 miles deep. That's about 12 times deeper than the Grand Canyon.
12 times on a tiny moon. How is that even possible?
It's staggering. And because Miranda's gravity is so incredibly weak, less than 1% of Earth, if you dropped a rock off the top of one of those cliffs,
Yeah.
it would take about 10 minutes to fall to the bottom.
10 minutes. Wow, just slowly drifting down. That's an alien landscape. What could have made Miranda look like that?
Good question. Theories range from intense tidal heating in its past that churned it up to maybe a catastrophic impact that literally shattered it and the pieces just clumped back together messily under their own weak gravity. It's a real geological enigma.
A 10-minute fall. Mind-boggling. Okay, but beyond the crazy surfaces, the most exciting idea about these moons now is oceans. Subsurface oceans. How realistic is that?
This is definitely the most exciting prospect, as scientists put it. The potential for hidden oceans. Based on computer modeling combining the Voyager data on size and density with calculations about internal heat, it looks plausible that 4 of the 5 main moons could have liquid water oceans.
Which 4?
Ariel, Umbriel, Titania, and Oberon. The model suggests they might have enough internal heat to maintain a liquid layer sandwiched between the icy outer shell and the rocky core inside. Miranda is considered less likely, probably too small to have held onto enough heat.
Okay, but where would the heat come from? They're so far from the sun.
Good point. Sunlight does basically nothing that deep. The heat has to be internal. Some could be leftover heat from when the moons first formed. Another source is the decay of radioactive elements within their rocky cores, slowly releasing heat over billions of years. Tidal heating, that gravitational squeezing from Uranus and the other moons, which powers volcanoes on Jupiter's moon Io, is probably less effective here. Uranus just isn't as massive as Jupiter or Saturn, so its tidal pull is weaker. So radioactive decay might be more important here than in the Jupiter or Saturn systems. It hints that maybe there are different ways to keep an ocean liquid in the outer solar system.
Different paths to an ocean. Okay, so if there are oceans, the next question is always life, habitability. What's the potential there, realistically?
Realistically, it's a long shot, but an intriguing one. For life as we know it, you need 3 main things. Liquid water? Check, maybe. Essential chemical building blocks, the CHNOPS elements, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, and an energy source.
Okay. Water check, maybe? What about the chemicals?
We expect the rocky cores could provide many of those chemical elements, leaching them into the water over time, potentially creating a chemically rich environment, like deep-sea vents on Earth.
And energy, if not sunlight.
Chemical energy. Reactions between the water and the rock, similar to those hydrothermal vents on Earth's ocean floor.
Yeah.
Life thrives there in total darkness, using chemical energy, not sunlight. That's a model people think about for these ocean worlds.
But it's cold, right? Even the ocean.
It would still be very cold.
Yeah.
Surface temps are like negative 200 degrees CO. The ocean would need to be significantly warmer, maybe hovering around freezing, perhaps warmer near potential vents. Even negative 20 degrees C is tough, but some microbes on Earth, extremophiles, can handle conditions close to that. So the potential is there. These moons could be this amazing laboratory for seeing how different moon systems evolve and if they can create habitable niches. A future mission would absolutely target this question.
Right, a future mission. Because, as we keep saying, we've only had that one quick look with Voyager 2 way back in '86. That really is a paucity of information, leaving these huge blank chapters. So after decades, what's the plan? Are we finally going back?
The wait has been long, yes.
Yeah.
That lack of data is a major driver now. No other spacecraft has visited since '86. There were even ideas floated about sending Cassini there after its Saturn mission ended, but the travel time, like 20 years plus costs and other priorities, meant it didn't happen. Outer solar system exploration, it really is a long game. Requires patience, planning decades ahead.
Decades indeed. But the scientific community seems united now. That decadal survey, the big NASA priority list, Uranus is finally top of the list, right?
Yes, that's the huge news. The most recent decadal survey for planetary science, covering 2023 to 2032, elevated the Uranus orbiter, and probed the UOP mission concept to the highest priority for new NASA flagship mission.
Highest priority. Wow, that's big.
It's monumental, a huge shift from the previous survey where it was third. It reflects both the lack of knowledge and the growing importance of ice giants, especially because of all those Uranus-sized exoplanets we're finding. The UOP concept is ambitious. A long-lived orbiter to study the whole system planet, rings, moons, magnetosphere for years. And critically, it includes an atmospheric probe.
A probe to drop into the atmosphere.
Exactly. To measure the composition, temperature, pressure, winds directly as it descends. That's crucial data you can't get from orbit.
Okay, so when might this actually happen? Launch. Arrival.
Well, the original hope was maybe a 2031 launch, using a big rocket like a Falcon Heavy, getting there around 2044.
Yeah.
But there are challenges. Specifically producing enough plutonium-238, the nuclear fuel needed to power spacecraft way out there where solar panels are useless. Production is ramping up, but there might be shortfalls. So a launch in the mid to late 2030s is looking more likely now, which means arrival wouldn't be until around 2045 or even later.
2045. Wow. So the scientists starting their careers now might be senior researchers by the time the main data comes back.
Exactly. It's truly a mission for the next generation to really get their hands on.
A multi-generational effort. Okay, what specifically do they want to learn with UOP? What are the big science goals?
They want to fill in basically all those blank chapters we mentioned.
Yeah.
For the atmosphere.
Yeah.
Map its 3D structure, figure out the circulation, how deep those crazy winds go. The probe is key here, getting that ground truth as it drops down maybe 5 or 10 times Earth's atmospheric pressure. For the interior, pin down the bulk composition, figure out if it's neatly layered inside, or if the core is more fuzzy and mixed with the ices, and get a precise measurement of its true rotation rate, which is surprisingly hard from afar. They even plan a new instrument, a Doppler imager, to look for subtle oscillations in the atmosphere that could reveal the structure deep inside, like seismology does for Earth.
Using sound waves, atmospheric waves, to probe the inside.
Yeah,
Cool.
for the moons. Get global maps, understand their geology, use spectrometers to map surface composition in detail, and crucially use magnetometers to look for induced magnetic fields.
Ah, the sign of a subsurface ocean.
Exactly. If a moon has a salty ocean, it'll interact with Uranus's main magnetic field in a detectable way as the moon orbits through it. That's a prime goal.
Yeah.
Plus using radio tracking to measure the thickness of ice shells, oceans, and cores. And finally, the magnetosphere. Really figure out its weird structure, how it interacts with the solar wind, the planet, the moons, especially after that Voyager bad day revelation. See how it behaves over years, not just hours.
It sounds incredibly comprehensive. And you mentioned the exoplanet connection. How does studying Uranus help us understand planets orbiting other stars?
Massively. If we connect this to the bigger picture, we found thousands of exoplanets now. And guess what? The most common type seems to be worlds roughly the size of Uranus and Neptune. Ice giants, or maybe sub-Neptunes. So understanding our own ice giants in detail gives us ground truth. It provides context for interpreting the limited data we get from exoplanets trillions of miles away. How do these planets form? How do they evolve? What are their atmospheres like? Studying Uranus helps answer those questions for a whole class of worlds out there. The UOP mission aims to understand the whole system, planet, rings, moons, magnetosphere, how it all fits together. That's invaluable for exoplanet science. And while Uranus got the nod, Neptune is still incredibly interesting too. A Neptune mission concept, Odyssey, was also studied.
What's special about Neptune compared to Uranus?
The big draw for Neptune is its giant moon, Triton. It's almost certainly a captured object from the Kuiper Belt, like Pluto. It has its own thin atmosphere, nitrogen geysers erupting, and maybe its own subsurface ocean. It's a whole different kind of world to explore. So lots of science to do at both ice giants, really.
Captured moon with geysers. Wow. Okay, so UOP is the big NASA plan. Is anyone else looking at Uranus? International partners.
International cooperation is definitely seen as key for these huge, expensive outer planet missions. Sharing costs, sharing expertise, building more capable spacecraft together. Collaborations between NASA and the European Space Agency, ESA, are common and could definitely happen for UOP. And China's space program is also showing serious interest in the outer solar system. Their Tianwen-4 mission is already planned to fly by Uranus around 2045, maybe on its way elsewhere. And there's talk of a potential Tianwen-5 that could be a Uranus or Neptune orbiter later on. So yeah, the future of outer planet exploration will likely involve multiple agencies working together.
Okay, so we've journeyed through the planet, the moons, the missions. Let's circle back to that ultimate question, life. On Uranus itself seems like a definite no-go, right?
On the planet Uranus itself. Yeah, that seems about as close to a definite no as you can get in science. The conditions inside are just too extreme. Crushing pressures, no solid surface, no plausible energy source for life as we know it.
An atmosphere.
Hydrogen, helium, methane, plus that lovely hydrogen sulfide. It's toxic soup. Highly, highly unlikely.
Right. Planet, no. But the moons, those potential ocean worlds like Ariel, Titania, what's the real hope level there? Still a long shot.
It's still a long shot, but it's where the most exciting prospect lies, for sure. The possibility of those subsurface liquid water oceans is tantalizing. But even if the oceans are there, habitability is another huge hurdle. They need to be warm enough, which is still very cold by our standards. They need the right chemical, mix the building blocks of life. And they need that chemical energy source, likely from water interacting with the rocky core, like those hydrothermal vents.
So lots of ifs.
Lots of ifs. We need to confirm the oceans exist, measure their properties, figure out the chemistry, detect signs of energy gradients. It's a huge undertaking.
So what's the general vibe among scientists? Optimistic, pessimistic?
I'd say cautiously optimistic. Maybe hopeful is a better word. You hear phrases like, appears highly unlikely, but we live in hope. Or, maybe, but we need data. They recognize the immense challenges, and as you said, the timescales are huge. The scientists starting out now will be the ones analyzing the data when they're deep into their careers. The next generation will really do the heavy lifting, as they say. But the drive to understand if life could exist in these hidden environments, so different from Earth, is incredibly powerful. It's a key part of understanding our place in the universe.
Wow. Okay, what a deep dive that was. We've gone from a mistaken star to a primordial god's dramatic backstory. We've explored a planet rolling on its side with crazy seasons, a magnetosphere that fooled us for 40 years, surprisingly dynamic weather, faint rings, and moons. From the chaotic jigsaw of Miranda to the tantalizing potential for hidden oceans under the ice of others. So what does this all mean? I guess it means our universe is just packed with surprises, right? And sometimes it takes decades, even centuries, plus a lot of ingenuity and looking at old clues in new ways to really grasp what we're seeing out there. That fleeting glance can be just the beginning of the story.
Absolutely. And maybe the biggest lesson from Uranus, especially that Voyager 2 bad day, is just how easily we can be misled by initial observations. It really underscores the need for patience, for persistence, for developing new ways to look and analyze. The cosmos is dynamic. It changes. What we see in one snapshot might not be the norm. It really makes you wonder, doesn't it? What other cosmic bad days might have skewed our understanding of other objects or phenomena just because we happen to look at the wrong moment? What stands out to you about Uranus and its future exploration? What other secrets do you think are waiting in those far-off icy depths of our solar system?